My name is Colin Hank, and today I would like to make this brief video. I'm not sure how brief it'll be, but this video to go over the first experiment. In a couple of weeks, when Mondays aren't holidays, I'll actually do these review sessions in person, and I'm also going to attempt to live stream those review sessions to give you the flexibility if you want to come in person and watch, or if you want to watch it online. The live streams will be available anytime after the session itself. So if you see me around, please call me Colin. And basically what I want to do today is very briefly go over what is required for the first lab and then get right into what we're doing in the first lab experiment. Now I know most of you have already written the pre-lab during your first week of lab, so I'm not going to spend quite as much time on that. But during the review sessions, we'll talk not only about the theory and what's going to actually go on in the lab, but we will also talk about some of the stuff that you need for the pre-lab, like the separation scheme, if there's some limiting reagent or something like this, some stoichiometry calculations and this kind of stuff. But for today, what I would like to go over is basically some general information about the lab, followed by the first experiment. So first thing, if we go into Blackboard and we go to lab materials required and first experiment, if you don't already have a lab manual, you can actually download a copy of the first experiment here. Also, what's required for this lab? A lab manual, goggles, a lab coat, gloves, and a scientific calculator. All right. The last thing, it's not really a required thing as far as something you have to buy, but make sure you're dressed appropriate for lab. The weather today is very, very hot, but when you come to lab, you still have to have completely covered legs and feet. So make sure that you are dressed appropriately for lab. We have a lot of rules. We don't want to send anybody home the first day, so please make sure that you follow these things. All right, now that I've gone over the basic rules quickly, I want to get right into the actual experiment itself. So for the first experiment, we're going to separate ethanol and 1-butanol. Now it's important to remember that chemists very often need to separate things by necessity. And in the first part of this course, you're going to spend a lot of time learning how to separate things. And these techniques that you learn, you will use again. In fact, the course is designed so that on purpose, you will use them again. So learning these things and understanding why they work and when they work is very important. And there are lots of separation methods that are available to chemists. And some work for some things and they don't work for others. That's why there's lots of methods. If there was a single separation method that always worked in all cases, that's the only thing we would teach you because everyone would use just that one. But that's simply not the case. So the reason there are so many separation methods is because some separation methods work well for some things and some work well for others. So in this case, we're going to separate ethanol and 1-butanol. And physical properties wise, these are both clear liquids. So if we look here, this is ethanol. It's a 2-carbon alcohol. This is the one that's in beer and vodka. And this is 1-butanol, which is a 4-carbon alcohol. So the only difference between this one and this one is that butanol has 2 additional carbons. Well, if we want to look at their boiling points, the boiling point of ethanol is lower than the boiling point of butanol. And you learn in general chemistry that these both have hydrogen bonding, which is a very strong intermolecular force. But 1-butanol has a higher boiling point than ethanol because although they both have hydrogen bonding, 1-butanol is a larger molecule and therefore has larger dispersion forces. That means the 1-butanol molecules stick together more. Said another way, you have to add more energy to separate them. Said in even another way, they have a higher boiling point. So boiling point essentially comes down to intermolecular forces. And here, the strongest intermolecular force again is hydrogen bonding, but the 1-butanol has the stronger dipole forces for the simple reason that it is a larger molecule. So a lot of the things you learn in general chemistry do come up again in organic. Now, what's important here is we are going to take advantage of this difference in boiling point in order to separate these molecules. And I mentioned before that separations are really important to chemists. So for example, commercial aspirin is synthesized using sulfuric acid. So if we're using sulfuric acid to make aspirin, when you go to the store and you buy bare aspirin, you definitely don't want any sulfuric acid in it. So sulfuric acid is absolutely necessary to make aspirin. However, it not wanted when you get the final product. So you have to get rid of it, you have to separate it in order to sell pure aspirin, even though you had to use sulfuric acid to make it. So here we're using some techniques that are for very specific cases, but these have very wide-reaching implications. In fact, distillation, okay, is actually done to vodka to purify it. So you can actually use distillation to get rid of some of the impurities in the vodka to make sure that it doesn't get people sick and stuff like this. So this is what we're going to do here. So now that we have an idea of the two molecules we're trying to separate, let's look at how we're going to separate them. We're going to look at two types of distillation, simple and fractional. But before we look at the difference between these two types of distillation, what I'd like to look at is distillation in general. So what are you going to do? You're going to take a mixture of ethanol and butanol, and you're going to put 20 milliliters of it in a 50 milliliter round bottom flask. So this will be a 50 milliliter round bottom flask, and you're going to put 20 milliliters of a mixture of ethanol and butanol in it. And you're going to do that for both the simple case and the fractional case. So you're essentially doing these both at the same time. You're going to work in groups, so person can set up one and one person can set up the other, or however you want to divide the work. But you're basically going to do the same thing to both. Now that you've got some sample in here, you're going to put what's called a heating mantle under here, and you're going to set the temperature to about 45% of the maximum. So 45 out of 100 or 60 out of 140. On the variac, do not plug the heating mantle directly into the wall. Plug it into the variac, which controls the amount of electricity the heating mantle is getting, and therefore the temperature. After a few minutes, you're going to want to make sure that it's turned on. But before you turn on the heating mantle, you want to make sure you have this entire apparatus set up properly. So essentially what's happening is you have your solution in here. You have what's called a distillation head here, which is just a piece of glassware specifically designed to connect this thing together. And you have a condenser here. For the condenser, you're going to hook this water inlet up to the sink, and this water outlet is going to go into the drain. And what you're going to do is you're going to gently flow water through here to keep this cool. So as you apply heat, remember you have this whole thing set up properly first. As you apply heat, what's going to happen is this liquid is going to heat up, and you're going to want to make sure that it's getting hot, because if the variacs are wet, they will not work. For safety reasons, they shut themselves off. So just make sure that yours is heating up. Then as it heats up, the liquid turns into a vapor, and it heats up this glass and heats up this glass, and all of this glass will be covered in aluminum foil, and the glass gets heated slowly, and eventually this gets hot. And then the vapor can make it all the way up to the top here. And then what will happen is this glass will be cold, and it'll condense. And when it condenses by gravity, you'll notice this is sloped down. By gravity, it'll fall into what's called the receiving flask. So this is the distilling flask, and this is the receiving flask. You'll notice that the receiving flask is connected by something called the vacuum adapter. Now you can do something called vacuum distillation, but we don't do that here. We do open air distillation, and you'll notice that there's an opening here. Sometimes students want to plug this opening, and this is a very, very bad idea. And the reason that it's a bad idea is because this has to be an open container. One of the worst things you can do in a chemistry lab is heat a closed container. Because if it's a closed container, pressure can build up, and if pressure builds up, it can explode. So make sure you leave this open. This is a way of equalizing the pressure and making sure that you're not going to have any chance of explosion. A couple other things to point out, and this applies to both simple and fractional distillation, even though I'm mostly talking about the simple distillation here, is the position of the thermometer. The thermometer is just barely below the neck of the distillation head. Here, you can get an accurate boiling point of the solution. If you stick this down into here, you're not going to get an accurate boiling point. You're going to get a boiling point of the mixture. This will give you an accurate boiling point of the sample that's actually coming off of the mixture and making it all the way up here. So this is basically how you're going to want to set this up. Now in a fractionating case, the only difference is we have this thing called a fractionating column. And I'll talk about that in just a minute. But you'll notice the rest of the distillation apparatus, including the position of the thermometer, the receiving flask, the condenser, the vacuum adapter and open to the air is all the same, but we have this fractionating column. So now that we've seen these two types of distillation, let's talk about the differences. Well, what does this fractionating column do? This fractionating column is actually a relatively simple thing that does an important job. When the liquid comes up into the fractionating column, it will condense, then it will boil again. Then it will condense, and then it will boil again. And then it will condense, and then it will boil again. So instead of doing like one distillation, you're doing multiple distillations where the liquid is evaporating, condensing, evaporating, condensing, evaporating, condensing as it makes its way up to the top. Said another way, there's simply more distance between the heat source and where the molecule has to get to. This increases the chances that the lower boiling point molecule will come out first. So the whole idea here is that the lower boiling point molecule will be more likely to make it to the top here and fall back down into the receiving flask. By adding more distance, and surface area too, between the heating source and where the molecule has to get to, we increase the chances that that will be the lower boiling point molecule. And believe it or not, this works quite well. From a general standpoint, what we say is, for simple distillation, we need a difference in boiling point of approximately 60 degrees. You'll remember that the boiling point difference between our two molecules is only 40 degrees, so we may not get good separation with simple distillation. Fractional distillation can be much better, although probably not perfect. It can be much better because of this increased distance between the heat source, and the surface area of course has something to do with it, between the heat source and where the separation actually occurs. Now here is the trick, the key to all of this. The key to all of this is to distill slow. If you crank up the heating mantle so that this distillation happens quickly, I promise you it'll happen faster if you crank it up, and everybody wants things to happen faster. But what's the problem? If you crank up the heating mantle, you're giving these molecules tons of energy. And when you give them this extra energy, you increase the probability of the higher boiling point molecule making it up and falling into the receiving flask. Said another way, you decrease the ability for this thing to separate the two molecules. So in the lab manual, it says you want to set this so it drips 1 time every 10 seconds. That's going to feel painfully slow if you've never done this before. Okay, it's going to feel like, holy cow, what am I waiting so long for? But if you get it to work at 1 drip every 10 seconds, especially with the fractionating column, you're really going to increase the chances of a separation. If you just crank up the heat, you're going to give the molecules way too much energy, and you're going to really decrease the ability to separate them. But if you keep the heat low, and you can tell that you have it appropriate because you have 1 drop every 10 seconds, then you should be good to go. So what are you going to do? Well, you're going to heat this up, and you're going to watch the boiling point up here. And what should happen is the thermometer, when this thing is dripping at 1 drop every 10 seconds, should read somewhere around 78, the boiling point of ethanol. Then at some point, the temperature should start to drop. And the reason that it starts to drop is the fractionating column and the distillation head will be somewhere around 78 degrees. So what's going to happen is, as the 1-butanol starts to come up, it's going to condense in there. And when it condenses, it's not going to reach the thermometer. And when it's not reaching the thermometer, the temperature starts to drop. So we know that we've pushed all the ethanol over when we see this drop in temperature. So when you start to see the temperature fluctuate, drop, what you want to do is remove the receiving flask. Because what that means is that the ethanol is done coming over. And now it's mostly butanol in here. And the heating mantle will boil the butanol, and it will start to come over as well. So when we see the temperature fluctuation, again, we remove the receiving flask, and we're essentially done. If you like, you can put a beaker underneath here, and you can continue this, and this should drop a lot. Okay, it should go down, 10 or 15 degrees before the butanol starts to come out. So that's essentially how the distillation works. So now we've gotten this separation to occur. So what are we going to do with the information? So we have this stuff in the receiving flask, which we assume is ethanol. However, we can't just assume that it's ethanol. We need to actually test and see what's in there. And to test and see what's in there, we're going to use something called GC, gas chromatography. So what gas chromatography is essentially a very fancy oven that has incredibly good temperature controls. So it's basically three ovens. So the first oven is what's called the injector port. So you're actually going to use a needle. It's an auto sampler, so you won't actually have to touch the needle, but you're just going to use a needle to inject about 1 microliter of your sample into this injector port. This injection port is very hot, so it vaporizes your sample. Your sample then goes into a 30-meter column. Now, there are lots of types of gas chromatography, but this type of gas chromatography that you're using here is essentially going to separate the molecules by boiling point. This oven is going to be at the appropriate temperature as tested empirically by us. So we actually figured out what the appropriate temperature was. That what's going to happen is helium is blowing through this column, and it's at appropriate temperature where ethanol will move through this column more quickly because it has a lower boiling point, so more of its molecules at any one time will be in the gas phase. This is a 30-meter column. If more of the ethanol molecules are in the gas phase, they will reach the detector more quickly. Then what will happen is the butanol will start to come out, and after the ethanol comes out, the butanol will come out. Then we use a detector. The detector that we use is called a flame ionization detector. Essentially what we do is we burn the sample. When you burn anything, you temporarily get ions. Those ions can be passed over what's called a collector, and you get an electrical signal. That's not super important. But what is important is you're separating the molecules by boiling point. So ethanol comes out first, butanol comes out second. So that's how the GC is going to work here. So that's the GC. Now, what do you actually get from the GC? Well, what you get from the GC is a chromatograph that looks like this. And it's basically got these little peaks, which are noise, and it's got two large peaks. So I should mention, this is the original mixture that we're collecting the GC of. And I understand this is a little fuzzy because this is actually a scan of the actual chromatogram that we got. But basically, you get two peaks. And again, this is the original mixture, so these peaks are about the same size in terms of area. Then at the bottom, you get this chart. And this chart is mostly what you're going to want to use. You'll notice that each peak has a number at the top of it. This number is called the retention time. It's literally the time that it took for that peak to come out. So on the x-axis, we have time. On the y-axis, we have picoamps, which is just an electrical measurement, again, from the collector. So we have ethanol in this peak, and we can see the time. And we have butanol in this peak, and we can see the time. Now I tried as best I could to blow this up. So at 2.550 minutes, that matches this number here, okay, we see ethanol. This is the area, and this is the percentage. So this is essentially 48%, 48.5% ethanol. Then butanol is here, and this is 3.197 minutes, and it's essentially 51.2% butanol. And then there's a little bit of other noise. That's normal. That's going to happen. Okay. But you could see the two major peaks, 48% and 51%, are the ethanol and the butanol. Now, I should mention to those of you who are chemistry majors especially, or people interested in doing GC later on, this is not directly allowed. You can't compare ethanol and butanol directly. You can relatively, and it works, but if you were actually going to do this, you'd have to do quite a lot more work to find the actual percentage of this and this more specifically than we're doing here. All right, so we're going to do 3 GCs. The TA is going to do one for you, and then you're going to do 2. So the original mixture, the TA is going to do for you, and that's what we just saw. 48.5% ethanol, the first peak, and 51.2% roughly 1-butanol, the second peak. So that's basically what we see in the original. We then do simple distillation. And this is just example data. Your data may not look exactly like this, but it's really important to remember that we need to be able to interpret data. The reason that scientists get jobs, one of the major reasons that scientists get jobs, is because data doesn't interpret itself. They need people to do that. So we need to be able to interpret this data and figure out what it means. So in the simple distillation case, the ethanol peak area is 63.5%, and the 1-butanol peak area is 35.4%. And again, you'll notice the retention times, they're not exactly the same, and this is real data that we collected, okay, but they're pretty darn close. All right, and they should be pretty close because they're the same molecule, ran on the same temperature program, so the retention time should be about the same. They're not going to be exactly the same. There's slight differences in the last decimal place, and you can argue whether that last decimal place is actually a sig fig and stuff like this, but what's important is that they're very close together. So what have we done? Well, in simple distillation, we find that there's more ethanol than in the original mixture, but there's still a heck of a lot of 1-butanol. Okay, so this is good in the sense that we've gotten more ethanol than we had in the original mixture, so we did something, but it's not that good because we still have 35% of our sample is 1-butanol. So simple distillation did not effectively separate these two molecules, right? It did separate them somewhat, but not effectively. So again, these numbers are numbers. What do these numbers mean? The numbers mean that, as I just said, that we've increased the amount of ethanol. Said another way, we've separated out some ethanol, but we still have a lot of 1-butanol, so it didn't work very good. Here's fractional distillation, and these are real numbers from us. This, in order to get numbers like this, you're going to need to have 1 drop every 10 seconds. If you have 1 drop every 2 seconds, you're going to see numbers much closer to this than this in the fractional distillation because you're just giving those molecules too much energy. So you have to go slow. And I believe me, it's going to feel painful when you're in the lab watching that thing drip 1 time every 10 seconds. That's 6 drips a minute. That's going to feel really slow. But if you do it slow and you do it well, it's only going to take about 45 minutes to an hour, okay, to do the actual separation, not the whole lab. But that being said, you're going to get nice data like this. A couple things to notice. Look at the retention times. Again, they're not exactly the same, but they're pretty darn close. 2.5, 2.5, 2.5, 3.19, 3.19, 3.19. They're really close. Okay, now let's look at the peak area percentage. The peak area percentage here is 93.5% ethanol and only 6% 1-butanol. So here we've much more effectively separated the molecules. Is it perfect? No, it's not perfect. Okay, but it's much more effective than simple distillation. So adding that fractionating column, adding that distance and surface area between the heat source and where the separation actually occurs makes a big difference. All right, fractional distillation is a much more effective method based on this data. Now, I've talked about the interpretation of this data. Please make sure that when you are writing your post lab, all right, writing your conclusion, you write based on interpretation of your data. If your data says 50-50 for all of these, don't draw the conclusion that fractional distillation is better, because in your case, it's not. So interpret the data you have. We would much rather you interpret the data that you have than you make perfect data. However, I've already told you the secret to making good data here. The secret is going slow, all right? Not adding a lot of energy. Last thing I want to talk about, and then we'll be done with this video, is the separation scheme. So this is the simple distillation separation scheme. In the distillation flask, before the distillation, we have ethanol and 1-butanol. Now, this is a bit complex as far as what should be in the receiving flask and what should be in the distillation flask. Now, in an ideal world, the receiving flask should contain ethanol, and the distillation flask should contain butanol, 1-butanol, right? We're gonna push the ethanol over to the receiving flask, and in the distillation flask, we're only gonna have the 1-butanol remaining. Remember that the distillation flask is here, the one we're heating up, so we're going to push all the ethanol over here into the receiving flask, and the 1-butanol is going to remain. And if you wrote that, it's okay. I mean, we're going to give you credit for that. Probably a better, more accurate way of writing this would be the receiving flask should have more ethanol and less 1-butanol, and vice versa for the distillation flask. It should have more 1-butanol and less ethanol. Okay, so that's basically another way of writing this. I know that people like to have, black and white answers. This is right and this is wrong. But this is kind of like writing a paper. When you write a paper, there's no one right paper and then a wrong paper, if you will. There's lots of good papers. Now, of course, there's lots of bad papers. But there's not just one right answer. So there isn't really one right answer here. If you wrote here ethanol, here 1-butanol, that's okay. But probably a little bit better again is the receiving flask more ethanol, and less 1-butanol, and again in the distillation flask more 1-butanol and less ethanol. So that concludes some of the basics for the first experiment. I do want to remind you that in this course, when you do quizzes and exams and stuff like that, what we focus on is the theory. So it's important to understand why distillation separates things, as we talked about in this video, how GC works, okay, and how to interpret the data, because this is what's going to be the lasting thing. Setting up a distillation apparatus and learning how to do that is very important, and it's essential for all chemists to do this. However, knowing what it means and why it works, to me, is the most important thing. So that's what we're going to focus on. One last thing. When we have review sessions in person, which again will be streamed live and available after the review session, so you can watch anytime, you don't have to watch live, we will focus a little bit more on actually writing the pre-lab. However, this week I know the vast majority of you have already written the pre-lab during lab, so we spend a little bit less time on that. Thanks for watching the video. I hope you found it helpful, and good luck in your distillations this week. Go slow, and it will go much better for you. Thanks for watching.